Hello, esteemed researchers, community, and honorable scientific committee. I am Ilgım Pekacar. I am a physics engineer and master's student at Istanbul Technical University in Turkey. I'm working on a project of quantitative examination of indentations in paper using 3D scanning. I'm glad to share with you my results. Firstly, I will explain what indented lines are, then the various methods used to detect these lines and how to detect lines with the 3D scanning method we use. Afterwards, I will explain the setup that is graded and analyzed with obtained results. Firstly, I want to talk about indented line. What is indented line and why detect these impressions? Forensic science examines suspicious documents that have the quality of evidence, and the depth of the lines is of great importance in the writings written on paper in these examinations. The bolt on the back of the paper may change depending on the pressure applied during the act of handwriting on or the surface under the paper. To detect the impressions in the documents to be examined, various approaches have been developed such as optical, electrostatic, and chemical procedures. The most common method still is used today is ESDA, that is electrostatic detection apparatus. It's a non-destructive approach that allows for additional testing. It's an extremely sensitive technology that can visualize indents up to 7 pages under the page where the original text is written. ESDA works by stretching a minor film over the document being reviewed. This minor film is electrostatically charged using a rod with a fine wire charged to 7 kV. In cases where the fibers of the paper are disrupted by paper-to-paper contact caused by indentations, the electrostatic charge is different from the background. This creates a latent image. Black toner is applied to the surface of the mirror to visualize this latent image. Toner preferentially adheres to places where electrostatic charge accumulates in indentation areas. The result is an image with a gray toner background and darker toner marks in areas with indented impressions. The image is made permanent as a removal by placing clear backed adhesive plastic over the toner, producing a stable, clear image. Another method is to photograph the indented lines of the paper under oblique lines. As the first step of this process, the indented prints in the document to be examined are photographed under one-sided oblique lines. The same prints are captured again, this time with oblique lines coming from the opposite direction. The position of the camera relative to the subject should be fixed as should the angle of the oblique light relative to the surface of the paper. The film is then processed, and the first and second negatives are carefully placed under a magnifying glass to create the final print. Negatives are carefully placed on a magnifying glass after being photographed with oblique light under the same conditions, but at right angles to the previous direction. In addition to these methods, traces can be detected using paramagnetic powder. A small amount of paramagnetic dust adheres to the resist surface when a stock magnet is used after the polyethylene sheet is applied on the document, so that paramagnetic powders do not stick to the document to be examined. As a result of paramagnetic dust in the resist area, the resist surface is now evident and fixed with adhesive clear film, then photographed for documentation purposes. In this study, the 3D scanner was used for scanning the lines for the first time. This is a non-destructive technique where the originality of the document is preserved, and the 3D image of the indentations was transferred directly to the digital environment without errors. In this way, the depth of the lines can be measured in micrometers, and it can be evaluated that whether the depth of the indented writing samples has changed after external indentation or not. For this method, samples were prepared on standard paper with a standard ballpoint pen. Then samples were created on different soils, both under constant pressure and under unstable pressure on hard and soft soils. A return table was prepared for scanning and the number of steps was set around 60 to obtain a clear result by taking more images of the sample placed on the table during scanning. Markers were placed around the sample for an accurate and simple 3D scan. Pointers are needed for accurate and simple 3D scanning. After that, the 3D scanner was also positioned in front of the table to remain stationary and provide the best view of the sample. After the number of steps, light brightness, and position are adjusted, scanning is started on the computer. After the scanning is completed, the 3D image we obtained is saved as a STL file, and software was developed in Python to measure the depth of the impressions on this image. Slowly closing the line is drawn over the depth line. According to the developed code, the cross line actually provides the coordinates of the X, Y, and Z axis on the 3D image. Since it was desired to find the depth, the coordinates obtained in the Z-axis were examined. After creating a graph with the Z-coordinates found, the background is removed with the slope equation and the depth of the traces on the paper on the newly created graph is obtained in micrometers. Immediately after this process, the sample is passed through the printer and scanned again in the same way, and the newly formed 3D image is analyzed. The results of analysis of different line samples were shown in figure. Photographs of the lines examined in the first row and depth profiles of the section between the points seen in the photographs in second row, and in the second row lines seen in plots represent depths measured before and after printing. The lines were drawn on soft surface where the additional 7 sheets were put under the paper on which the line was drawn. The initial depths of the lines were around 120 and 180 micrometers for horizontal and vertical lines, and it was about 90 micrometers for circular line. The change in depths of lines are due to the different temperatures during the preparation of the samples. After passing the papers through the laserjet printer, it's clearly seen that the depth of the lines decreases to the range of 1/3 to 1/4 of the initial depths. This decrease is mainly to the high pressure and high temperature in the drum of the printer. It can be said that, since the depth variations could be clearly observed for all samples, the 3D scan-based technique doesn't depend on the shapes of the lines drawn on the paper. The sample seen in the figure was prepared on a hard surface and almost no change was observed after passing the sample through the laserjet printer. The reason why almost change was observed after passing the printer, although the depth reaches 80 micrometers, may be related to the shape of the groove of the line. The groove of the line is probably not very wide, and therefore the drum of the printer is not very effective. This line is prepared on a soft surface and passed through multiple printers. The initial depth of the line was measured about 100 micrometers as seen in figure. After passing the paper through the printer for the first time, the depth dropped to around 40 micrometers, and further printing seemed to have almost no effect on the depth of the lines. This is an interesting result that shows that the first print probably causes a more rigid groove structure on the paper, which preserves itself during the other printing. The dependence of the depth of the lines on the pen pressure was also studied, and the results are given in figure. The depth profiles clearly show that the 3D scan technique is sensitive to the pen pressure change, where the depth of the lines was changed from 30 micrometers to 140 micrometers by increasing pen pressure. Consequently, in this study, a 3D scan-based optical technique was proposed for the analysis of the indentations in the question documents. It was concluded that this technique is reliable, fast, non-destructive, and enables a quantitative analysis. By using this technique, the grooves of the lines could be successfully observed and the depth profiles could be successfully obtained in the study. The effect of the printing on the depth of the grooves was carried out, and and it was concluded that while depth of the grooves of the lines prepared on the soft substrate changed considerably after the printing. The effect of the pen pressure on the depth of the grooves was also studied, and it was observed that 3D scan-based technique is very efficient to monitor this property of the lines.